geographic information systems, and we're gonna discuss some of the principles and application of remote sensing. What is the course program that we're gonna cover up? There are two sections of this course. In the first section, we're gonna talk about GIS basics. We're gonna discuss what is GIS. We're gonna talk about the definition. We're also gonna cover up some data types. Especially, we're going to talk about raster and vector data, which are the most common data types in geographic information systems. The parts of a geographic information system, as we know, the word is composed by three terms: geographic, information, and system. Geographic means that it's georeference. It has a position, coordinates, projections, data. And information system, that means that it's based on host on a software. A printed map does not qualify as a geographic information system, but a georeferenced and digitalized map can be qualified to be part of a geographic information system. Later on, we're gonna cover up software intro. I wanted to be a little bit more innovative. I didn't want to talk about the same open source or paid software. I wanted to explore a new alternative, a third way, so you'll have as many options as possible when working with GIS data. Then in that software, we're gonna work with raster and vector data. We're gonna see the metadata. We're gonna see all the options of the software. We're also going to perform some calculations on some raster and vector data, and we're going to find out which processes can we apply to each type of element. Later on, we're going to work with open data sources. We're going to find topography open sources, LiDAR open sources, world imagery open sources. Depending on your country, you can also have weather data, you can have terrain data, you can have satellite imagery, and all types of data. And we're gonna cover up one of my favorite GIS applications, which is the Web Map Services, which are it's a tool that we can use with a link provided by the supplier where the data is hosted. We can work with GIS data everywhere in the world, just having an internet link and internet connection, of course. Later on, after we've covered up all the GIS basics and that you are now a savant in this area, we're gonna pass on to its applications, which is for me the most important part, because we can know something, but we need to know how to apply it in the real world and how it can be useful and how can we solve problems with the GIS data. For example, we're going to discuss some applications in surveying. That means creating digital elevation models, digital terrain models, digital surface models, contouring, 3D models, and exporting our data. In hydrology, we're going to perform a watershed analysis using this software. Later on, we're going to see a little bit of LiDAR technology, which is very, very innovative and very hot right now because the self-driving cars are using LiDAR technology to scan the city or the routes from which they're passing through. So this technology is definitely going to be very booming in the next years. So it's very important to understand first what LiDAR means and how can we apply LiDAR data. And furthermore, we can learn in this course how to process LiDAR data. Then we're going to cover up the drone data processing, the UAV data processing. For the LiDAR part, I include a theoretical basic. For the drone part, the UAV part, I'm going to start directly to process the data, but as I process the data, I'm going to explain what photogrammetry is about and how can we use it. Then finally, we're going to cover up some aspects of telecom, from visualization, visual sheets, and we're going to perform some heat maps to understand what does they mean and how can they be useful for us. What do I expect you to learn in this course? First, working with raster and vector data, work with open source data and web map services, generate digital terrain models, contours, to process LiDAR data, to process UAV data for photogrammetry purposes, to create heat maps and telecom applicated maps, to perform watershed analysis, to export data in more than 300 formats or understand and work with more than 300 data formats, and so much more. So I really hope you can enroll to this course, that you will find it useful. I think it's a very important tool that we need to manage right now, even if we're students, surveyors, hydrologists, geologists, any person that works with georeference data needs to understand and to explore several new ways or new methods or new software or new applications of the GIS data to improve your current professional field and to improve your professional path. So I really hope you like this course. I've worked a lot performing some data examples. We're going to work with real life examples, not just theoretical information. In the application part, I'm going to explore and I'm going to use some real life scenarios and see real life data. So I hope you really enjoy this course. So let's start right now with the first part, the GIS basics that we need to cover up to understand the rest of the course. A geographic information system, that we will call GIS after this, it's a computer-based system that it's used to collect, store, manage, analyze, and display spatial or geographic data. As I said, we use in science the GIS to examine spatial relationships, patterns, and processes, and we can apply it to a broad range of phenomena, physical, biological, and cultural. That's the beauty of it. It has such a wide range of applications, and all you need to is understand that you can have information that is georeferenced, and from that point on you can elaborate several types of analysis that will help you take decisions or understand the current status of a certain situation or phenomena. The most common data types are raster, vector, points, lines, and polygons. We need to understand, we need to differentiate and separate different types of data. We can have raster data, which is grid data, which is most commonly images that contain pixels. We're later on going to explore a little bit more what does this mean. But we can work with images that are georeferenced. We can work with vectors, which are geographical features such as points, lines, or polygons. So anything can be expressed or as a raster or as a vector. For example, a tree has a geographical position and some characteristics or attributes. So we can express a tree as a point in space. A river can be expressed as a line with a certain sinuosity, direction, length, and coverage area. The state lines can be expressed as polygons, which are different subdivisions of a territorial land. Later on, we're working with a reference system. All our data has a framework, a reference system that contains it and helps us to position it in space. The basis of any coordinate reference system is a model of the Earth on which locations can be defined. We can think of the differences between globe models as being analogous to difference in globes you've actually seen in your life. Some are perfect balls, while others are spheres with elevations. Others might capture the full weirdness of the Earth's shape. There are several types of reference systems. For example, we have a geographic coordinate system, which is a global or a spherical coordinate system, such as latitude, longitude. Each point in space has one latitude and one longitude. It can be expressed as west or east for the longitude data and north or south for the latitude data. We can also have a projected coordinate system in which the system provides various mechanisms to project maps of the Earth's spherical surface onto a two-dimensional Cartesian coordinate plane. Projected coordinate systems are referred to as map projections. These try to flatten the Earth as much as possible, so the coordinates are not unique, are based on a certain stripe. The Earth is divided in several stripes or UTM zones, for example, and then each point has a certain coordinate in that stripe or in that zone. And as you move from zone to zone, you might have repeated number coordinates, but the zone differentiates them. What we're trying to do in those cases are to subdivide the Earth in as many flattened stripes as possible. For example, the Mercator projection is a cylindrical map projection presented by the Flemish geographer Gerardus Mercator. It became the standard map projection for nautical purposes because of its ability to represent lines of constant course as straight segments that conserve the angles with the meridians. We have also, the most common projection system, it's the UTM, the Universal Transverse Mercator. It's not a single map projection. The system instead divides the Earth into 60 zones, each being a 6-degree band of longitude, and uses a second transverse Mercator projection in each zone. We have also Olbers equal area, a conic equal area map projection that uses two standard parallels. Although scale and shape are not preserved, distortion is minimal between the standard parallels. As some important remarks for these first cars of the course, we have discussed what is GIS, how can we define it, which are the different data types, and as we know, we need to reference our data into a framework, which is the reference system. These are the parts that compose mainly a geographic information system, as well as the software and all the analysis that we can perform from them. In the following classes, we're going to cover up the data types and how can we work with